Welcome back to our chemistry video class. Topic compressibility factor Z. Deviation of real gases from ideal behavior is measured in terms of ratio of PV to nRT. Mathematically, it is written as Z equal to PV by nRT. P means pressure of gas, V volume of gas, N number of gas molecules or gas constant, T temperature. At all temperatures and pressures for ideal gases, compressibility factor Z equal to 1. Hence, PV equal to nRT. When a gas deviates from ideal behavior, compressibility factor Z deviates from unity. So, Z not equal to 1, hence PV not equal to nRT. Already I said, under certain conditions, real gases also approach the ideal behavior. What are the conditions? At very low pressures and very high temperature, all gases compressibility factor approaches unity. So, all gases behave as ideal gases. For these gases, we draw a graph between compressibility factor Z and pressure P. For ideal gases, this graph is straight line parallel to the pressure axis. From this straight line graph, what we'll understand? For ideal gases, compressibility factor Z equal to 1. So, PV equal to nRT. For ideal gases, the graph Z versus P give straight line. But for non-ideal gases does not give straight line graph. For example, nitrogen. Nitrogen is a non-ideal gas. For non-ideal gas, compressibility factor Z not equal to 1. So PV not equal to nRT. So for nitrogen gases, this graph does not give straight line. This is a curved line graph. See the gas molecule filled container. At low pressure, single gas molecule volume is very low when compared to the volume of container. So, individual gas volume is negligible, and also gas molecules are so far apart from each other, and hence attractive force also negligible. At low pressure, what happen? At low pressure, volume of individual gas and attractive force are neglected. But pressure increased, density of gas also increased because pressure and density are directly relation. So at high pressure, density also increased. And at high pressure, the gas molecules are much closer to one another. Hence, the intermolecular force between these gases becomes significant enough to affect the motion of gas molecules, and hence the gas will not behave ideally. So, at high pressure, the gas molecules density increased and molecules much closer to each other and significant intermolecular force to affect motion of gas molecules. These points indicates gas molecule does not behave ideally at high pressure. When temperature increased, the average kinetic energy of gas molecules also increased. Hence, intermolecular attractive force will very low. Hence, at high temperature, the average kinetic energy of gas molecules is very high, and hence intermolecular attractive force will become insignificant. But when temperature decreased, the average kinetic energy of gas molecules also decreased. Hence, intermolecular attractive force will become higher value. So, at low temperature, the gas does not behave ideally. In which temperature real gas obey ideal gas law over an appreciable range of pressure is called Boyle temperature or Boyle point. Boyle point depends on nature of gas. See the graph between compressibility factor Z and pressure P. In this graph, center curved line is Boyle temperature. Above the Boyle temperature, compressibility factor Z increases with increasing pressure. So, Z values always greater than unity. So real gases show positive deviation, but below the boiling point, Z value decreases with decrease in pressure and reaches a minimum and then increase with increase in pressure. So below the boiling point, first Z value decreased, then reaches minimum and then increased. So real gases behave as ideal gases when at low temperature and high pressure. Next, we will see compressibility factor for real gases. Already we know compressibility factor for ideal gases is equal to PV by nRT. For real gases, we substitute V real instead of V in Z ratio. So, Z equal to PV real by nRT. In this value, right side part P by nRT goes to left side. So, V real is equal to nRT Z by P. We know V real is equal to Z nRT by P. Now substitute V ideal value in V real value. So, V real is equal to V ideal into Z. Therefore, Z equal to V real divided by V ideal. Here, V real is real gas molar volume. V ideal is molar volume of its ideally. Next video class, we will see van der Waals equation. Thank you, students.